A comparison of data augmentation techniques for Nguni machine translation systems. Whilst machine translation quality has seen great improvements in recent times, high-quality translation systems require large volumes of parallel data to train. Parallel data is sentence-to-line bilingual text in both the source and target language of translation. Unfortunately, for South African languages such as the Nguni languages of IsiZulu and IsiXhosa, such volumes of parallel data are not readily available, leading to the question of whether it is possible to train machine translation systems on augmented data, leading to significant improvements in Nguni machine translation systems. As such, our project compared three types of machine translation systems, namely a baseline system, a back-translated system, and a multilingual system. The baseline system saw us simply train machine translation systems using data sourced from online databases such as the Sadler Repo and MEMAT project. The back-translation systems saw us build a Nguni to English primitive translation system and use that to translate Nguni monolingual data into English data, creating a set of synthetic or self-generated parallel data to add onto our original parallel data sourced from the internet to train our machine translation systems on. Then finally, the multilingual systems saw us train our systems on a combined IsiZulu English and IsiXhosa English dataset. Our project had a statistical machine translation and neural machine translation component. Prior to the advent of neural networks, statistical machine translation was the state of the art. This method made use of probability distribution-based models to perform translations. As such, in this project, the SMT systems built were built using the Moses Decoder Toolkit, KenLM language modeling toolkit with a 6-gram language model, along with the GIZA++ word alignment model, and they were phrase-based SMT configured, as phrase-based statistical machine translation is the most widely used form of SMT.
For all three models, we'll be making use of this English sentence. If we cannot solve them immediately, we'll give reasons and tell the client when a response can be expected for demo purposes. This sentence correlates with the 4 Zulu candidate sentences listed in the note open to the right of the screen. Currently, on the left, we are open to the Zulu baseline model. Passing that sentence into the baseline model, we come out with an answer that reads, as can be seen in the highlighted section on the left. Just quickly looking at that highlighted section and looking at the 4 candidate sentences, you will see that there are not a lot of congruencies between the two. This does indicate that this is not the strongest of models for IsiZulu. This theory is further supported by the BLEU score that one receives when they run the BLEU matrix, assessment matrix through a translated body of work from this model, yielding a BLEU score of 0.1923. The highest possible BLEU score is at a 1 and the lowest possible is at a 0. And so you can see that this does fall lower than probably is ideal. Now, passing in the same sentence into our back-translated model, the output sentence received is as shown in the highlighted section. With this translation, you can see much more congruency between the 4 candidate sentences and the sentence that appears on your screen. As a Zulu speaker, I can also say that that is a more fluent translation of the English than the first case, than the first model. With this in mind, we'll look at the BLEU score for this model. And we'll see that the BLEU score for this model is significantly higher than the baseline model, showing that this is a better model for translating IsiZulu in general. Finally, we'll look at the multilingual case. Again, we have the English passed into the model, yielding a best translation as seen below. This is vastly different from the 4 candidate models that we see on the left, showing that this model is likely the weakest of all 3. This is further supported by the BLEU scores that we receive when analyzing a body of work, a body translated, a body of text translated from this case, yielding a BLEU score of 0.15, which is the lowest of all 3 BLEU scores. This was the case in the Zulu context. The multilingual model did have the worst performance. However, in the Xhosa case, it had better performance in the baseline, but throughout, the back-translated models outperformed all other models.
In this part of the project, we compared the performance of baseline neural machine translation models against model trained using 2 data augmentation techniques. The first technique involves making use of the target side monolingual data to augment the amount of parallel data via back translation. And the second technique involves training a multilingual model on a joint set of bilingual corpora containing a combination of 2 languages, namely IsiZulu and IsiXhosa. Neural machine translation is a recently introduced paradigm that has achieved state-of-the-art performance, outperforming traditional machine translation methods. It models the machine translation process by using a single large neural network that takes as input a sentence and outputs its corresponding translation, one element at a time, in end-to-end fashion. This allows all the parameters of the model to be simultaneously changed to maximize translation performance. We use a Fairseq modeling tool to implement the different NMT models. These models were initially trained using Google Colab and a combination of GPUs. The CHPC cluster was also used to significantly reduce the training time of the models. The baseline models took around 3 hours to train, whereas larger models such as the back translation and multilingual model took around 6 hours. We compare the performance of the different models in terms of their BLEU scores. We now show you translation using our baseline English-to-IsiXhosa model on the CHPC cluster using command line. We can use a model that we have already trained interactively by using the Fairseq interactive command. We can type the input sentences to get their corresponding translations. For our back translation model, we train a reverse model to translate the target language into the source language over the target side monolingual data. This model was trained for 15 epochs and a patience of 5 was used to stop training if validation performance did not improve for 5 consecutive runs. Another model was then trained over the parallel and back-translated data with English as a source language and IsiXhosa as a target language. Similarly, this model was trained for 15 epochs and with a patience of 5. For the multilingual model, we used both IsiXhosa and IsiZulu as target languages and English as a source language. An artificial token was added at the beginning of the input sentence to specify the target language. This process allows multilingual translation without the need to modify the neural machine translation architecture. The encoder for the source language was shared and different decoders were used for the target languages. By sharing the encoder, the model makes full use of the source language corpora and learns semantic and structured predictive representations.